this lecture, I will explain factors affecting the speed of a DC motor. So generally the back EMF equation of a DC motor is 5Zn by 60 into P divided by A. Once design is over, number of poles is constant, number of parallel paths is also constant, and Z is the number of conductors is also constant, 60 is also constant. We can say that it is EB is directly proportional to N5. And from this equation, we can write it as EB is directly proportional to, EB is directly proportional to N5 and N is directly proportional to EB divided by 5. The speed of the motor is depends upon back EMF and flux. The EB can be written as V into IA plus RSC divided by 5. If you go for the shunt motor, this value is 0. If you go for the DC series motor, RA and RSC is also present. And neglect this drop. Why? Because RA is small and RSC is also small. RA and RSC is small. And I can write it as N is directly proportional to V divided by 5. The speed is depends on the first factor. The factors, yes, the factors affecting the speed of a DC motor, affecting the speed of a DC motor is the first one is the flux, and second is voltage across the armature, voltage across the armature, and third is the applied voltage, so we can go for the flux control method, and also voltage which across the armature also we have to control. By varying this, we should control the speed of the DC motor. So why we are going for the speed of a DC motor? So based on our requirement. Suppose generally I am giving the example of a fan. Yes, fan is working with AC supply. Anyway, since summer season you require more air. That's why you kept the regulator at 5 position. At winter, you kept that regulator at 1 position based on your requirement. So similarly, same way, based on the application, we can go for the speed control of DC motor also. For that, the speed of a DC motor is depends on supply voltage and flux. And the next concept is rating of DC motor. What is the rating of DC motor? The first one is the maximum voltage. The maximum voltage can be applied to the motor safely. To the motor safely is called rated voltage. That is the first one. And the second one is the maximum current flowing through field. The maximum current flowing through field winding safely is called rated field current. Is called rated field current. Okay, and if you observe, n is directly proportional to V divided by 5, and this is a V rated voltage. We know that flux is directly proportional to field current. Suppose if you draw the DC shunt motor, the current which is flowing through the field winding is IF, sir, no, and the armature voltage, the voltage which is applied across the armature is V. So V rated divided by IF is also rated. Then we can say that the speed is also rated. So what is the rated voltage? Means the maximum voltage which we can armature apply to the armature or motor safely, then it is called as a rated voltage. The maximum current flowing through the field winding safely is called the rated field current. Then if these two are rated, then the speed is also rated. The first concept is speed control of DC shunt motor. So for the first method is flux control. So I am drawing the shunt motor. I am connecting an external resistance that is called the rheostat. It is a variable resistance. So here, for every time you should remember, the armature should be in parallel with the field winding only. It has useful meaning. So this is at start. Here I am giving the supply voltage, and that too it is rated voltage. The field terminals are F1 and F2. The field winding resistance is RSH. So coming to the flux control method, initially it is at start position. If the variable point is at this position, no resistance is included. The external resistance will be 0. Only the field winding is present. The supply voltage will be applied across the field winding. That ISH is equal to V rated divided by RSH, and ISH is also rated. If ISH is rated, flux is also rated, then N is directly proportional to EB divided by 5, and this one is rated, and EB is also rated, and speed is also rated. And EB means V minus IA into RA. As I just now, as I said, EB is equal to V minus IARA. Neglect this drop, and EB is approximately equal to V. EB is approximately equal to V. And if a voltage is rated and the flux is also rated, the speed is under rated condition. The speed is called the rated speed of the motor. Then you should vary the variable position. That means resistance is increases. Once it will be at this middle position, this number of tons is included. Let us say this resistance will be R1. Now this is external resistance. ISH is equal to V rated divided by RSH plus R1. With this, the shunt current will be decreases. If a shunt current will be decreases, speed is also decreases. We have one relationship EB by phi, and EB is equal to V minus IARA. So as I am telling that load is constant. So load is constant means torque is constant. So load torque is constant. So torque is directly proportional to flux into Ia. Okay. So as flux decreases, what happened to the speed of the DC shunt motor? The speed of the DC shunt motor is increases. Then again, an external resistance is increases further. So it is moves like this. This is a third position, first and second, third. Entire resistance is included. Entire resistance is included. Then, if the resistance is increases, the shunt current will be decreases. The flux is also decreases. Why? Because the flux is directly proportional to field current. N is directly proportional to EB by phi. If flux is decreases further, the speed will be increases. If you draw the characteristics between speed versus flux, and that is ISH. If ISH increases, flux is directly proportional to ISH, the speed will be decreases. Speed will be decreases. It will follow the in reverse manner. For this, ISH is more. If ISH is decreasing in this manner, ISH will be decreased, then the speed will be increases. The shape of this waveform is looking like a rectangular hyperbola. Okay. So at this shunt current is 0 means dangerously high speed. As the shunt current increases, when the shunt current increases, as the external resistance will be decreases. So this is in the reverse manner. See, at this position you can observe only at first position. So at first position, the external resistance is 0 and ISH is equal to V divided by RSH. So this is a rated speed, as I am getting the rated speed. So what are the advantages of flux control method? If you can observe, the flux will be decreased the rated value, then the speed is greater than the rated value. So it provides relatively smooth rated speed is possible. Smooth rated speed is possible. And the second one is speed control is possible, that is above rated speed is possible. Above rated speed is possible. As the field resistance is high, the field current is very, very small, and the power loss, that is copper loss in field winding, is also small. And the next advantage, as the field current is small, IF is small, the size of rheostat is also small. The size of rheostat required is small. Next, disadvantages of flux control. Not only what is the first disadvantage, we can go for the above rated speeds, we can't go for the below rated speeds. We can't go for the below rated speeds. So that is the first disadvantages. The speed control below rated speeds are not possible. That is the first disadvantage. And the second one, if the flux will be decreases, speed increases, so it will affect the commutation process and the motor will goes to unstable region. Okay, there is a limit for the maximum speed. And the next method is armature voltage control. So armature voltage means I am connecting a resistance, that is called the rheostat, in series with the armature. This is called the start position. So minimum position, F and FF, supply voltage, rated voltage I am applying. N is directly proportional to EB divided by 5. Here the shunt current is constant. We are not connecting any variable rheostat in series with the field. ISH is constant. Then flux is also constant. N is directly proportional to EB. N, the back EMF is equal to V minus IA RA under normal operating condition. See, when it is at start position, this is a line, no external resistance is included, RE is equal to 0. The EB value is also rated, V is also rated. Then if IA is taking as per load requirement. So if it is under no load condition, this is rated. Under full load condition, yes, the EB value is changes, right? Once this resistance is included, external resistance is included in series with the armature. Now see the drop. EB2 is equal to V minus IA into RE. Then this drop increases, then obviously the back EMF is decreases. Since N is directly proportional to EB by 5, and for this motor N is directly proportional to EB, as an external resistance is increases and RA plus RE is also increases, then IA into RA plus RE increases, then the back EMF decreases. Yes or no? Because V minus IA into RA plus RE, and this term is increases and back EMF will be decreases. So if you draw the curve between speed versus the voltage which is applied across the armature or EB, so I am taking the normal speed under normal operating condition. with external resistance is 0. External resistance is 0. If I am increasing an external resistance, the speed will be decreases. So this is called the below normal speed. I have no other option to increase the speed above rated speeds, and for a constant load torque, n is directly proportional to voltage across the armature. The flux is constant. What is the disadvantages means? Okay, up to zero, speed is not possible. Not possible by this method. Possible by this method. This is a major disadvantage. Major disadvantage. And one more thing, IA is a load current, then IA square RA plus RE is a large losses are produced and the external resistance and armature. That's why we are going for the anyway. Yes, anyway we are losses are produced. We can go for the potential divider control. So potential divider control. So this is a field winding, and the armature winding is connected like this. So here the armature is connected. This is at start. This is at maximum. You can connect across a supply. You can connect across a supply. So the current flowing through is shunt current RSH here. Initially 0 volts. See, 0 number of turns are included. The 0 volts will be applied. N is directly proportional to EB by phi. The phi is constant. Then N is directly proportional to EB. If a voltage is 0, there is voltage across the armature. If voltage is 0, then armature speed is also 0. If voltage will be increases, the speed is also increases. So below up to 0, the speed is possible. This is a normal speed. Normal speed. If you draw the curve between the speed versus rated voltage, this is called the rated speed. The voltage corresponding to rated speed, or rated speed corresponding to rated voltage. So observe that the zero speed is also possible by varying this field rheostat. We can say that it is called the potential divider. We are connecting a three terminals. Two are the fixed terminals and another one is a variable. So potential divider control, if we go for the potential divider control, we can go for up to zero speed. And this method is very smooth. This is the advantages. And in a potential divider arrangement, this is smooth speed control, potential divider arrangement. Rheostat can be used as starter. And the disadvantages are, as I already discussed, armature copper loss is more, and speed above rated speeds are not possible. Above rated speeds are not possible. Speeds above rated speeds, large power losses, due to the large power losses, due to the large power losses, this method is expensive. This method is expensive, wasteful, and less efficient. Okay, and then we are going for the applied voltage control. The last method for DC shunt motor is called the applied voltage control. So in this applied voltage control, we can use the separate excitation for field, separate excitation for armature. Okay, we can say that it is called as a multiple voltage control. Multiple voltage control. So here this is plus 20 220 volts, the middle line is 0 volts, and another line is minus 220 volts. So I am giving the first 220 to first 220 to is given to the field winding. This is F1 and F2, and this is 0 volts, and from this 220 also I am taking, and this 220 also, and this is from minus 220. So this is given to armature. This is your armature, the motor A1 and A2. So I am representing the another lines. Yes, this is armature. See, two working voltages we can apply. When the armature is supplied with the various voltages, as if the switch is closed here, only the 220 volts is applied. 220 volts is applied. Let us say this is first position, second position. At first position, speed is directly proportional to 220 volts. The field winding is excited with this and there is no field rheostat in the field winding. The field current or field current is rated, because IF is equal to V by RSH or V by RF, and field winding is connected like this. If the switch is at position as n is directly proportional to 220, if the switch is at second position, you can observe 220 minus of minus 220, your voltage is 440. So n is directly proportional to 440. So if a voltage increases, then the speed is also increases. We can go for these multiple voltage controllers whenever the speed control is required. But here we require two supplies. One is a plus 220 and another one is minus 220. That is the disadvantages. I think you understand. This topic is very easy.